Okay, you're going to take notes on this PowerPoint here for energy. So one person should let this run on their iPad in your group, and then the other people should be taking notes in Notability. Those of you who are letting your iPad be used to show this slideshow should be helping make the notes on somebody else's, and then you can just share that note with each other. So title your note Energy, and we're going to talk about the forms of energy and how energy is conserved. Okay, as you can see here, there are 8 forms of energy. They're listed down the side. Make sure you get those into your notes: mechanical, electromagnetic, chemical, nuclear, light, sound, heat, and deformation. That means to deform something. And what I want you to do is see if you can match up each of these words with these pictures over here. And we're going to see, how you do, what you know already. So go ahead and try that with a group. See if you can match those up. Here are some examples of the 8 forms of energy. As you can see, mechanical would be like riding a bike. Electromagnetic would be wireless communication, so like your cell phone. That works on electromagnetic radiation. Chemical would be putting Mentos into a Diet Coke. Maybe you've seen that on YouTube. If not, you could always look that up. It's pretty neat. Nuclear, as you can see, is pointing down to the sun. Light energy, something like solar panels, or something as simple as a light bulb. Sound is a speaker vibrating music. Heat is like cooking food in a pan. And then a car crash or anything that has a solid that is deformed would be deformation energy. So conservation of energy just means that all the energy that there ever was and that ever will be is here now. So it can transfer from one form to another. You can look at the list again on the last slide. And we're going to talk about this concept of work next class, that doing work on an object is one way to transfer energy. So make sure you get these 3 bullet points down in your notes, and then we're going to talk a little bit about how that energy is transferred here in just a second. Okay, let's talk about energy transfer. Let's say something as simple as eating. You've got a plant that's growing, and I don't know, maybe you get like an apple or something, or some sort of tomato or fruit or something from that, and then you come along and you go, ooh, I'm hungry. I'm going to eat that food, and then later I'm going to go for a run. So what are the different types of energy that we had? Well, we've got the sun energy coming in to help the plant grow. We've got some sort of chemical energy happening on the inside of that plant, like you learned about in biology. We've got energy in the form of calories in the food that we eat, and we chew it up, and again, that goes back to some sort of chemical energy that allows our muscle to move, and then that turns into mechanical energy as we run. So energy is just transferred. It's never created and never destroyed. So mechanical energy is mostly what we're going to be dealing with in this class. Somebody running, or a roller coaster physics, things like that, where we're talking about objects that are in motion, and we can talk about how fast they're going or how high off the ground they are. And having said that, potential energy which we call PE, has to do with how high off the ground you are. And kinetic energy, which we call KE, has to do with how fast objects are moving. So mechanical energy is here. The total mechanical energy is when you add those two things together. Gravitational potential energy, that just means that how far away you are from Earth up in the air, and then kinetic energy, which is how fast you're moving. So the equation for gravitational potential energy is here. It's PE, potential energy, equals mass times gravity times height. And h is the height above or below a reference line. Ignore these z's here. I don't know when it transferred into this program. It didn't understand my little markings there, so just ignore that. So let's say in this case that the ground is 0, like how I have this drawn here. There's a little line down here. And I have a ball that's drawn and it's sitting on the ground. What is the height of that ball? The height is 0. So if the height is 0, that means that your potential energy for that ball is going to be 0 joules. But what if you take that ball and you lift it up off the ground? So the first example was a ball sitting on the ground. We have a potential energy of 0. But now if I take that ball and I lift it up a little bit so that there's some height here, my potential energy is not 0 joules. Now it would be dependent upon the height, and to find it you would take mass times gravity times height. So here's an example. If I have a ceiling and I'm saying that the floor is at 0, so my floor here is at 0, and the ceiling is 3 meters high, and I have a ball hanging from the ceiling that is 1 meter down. So the length of the string is 1 meter, and the ball hanging is 2 kilograms. I can figure out the potential energy by just taking mass times gravity times height. And in this case, I'm calling gravity 10. So I get an answer of 40 joules. But now let's say we take and we move the reference line. And now we're no longer saying that the floor down here is 0 potential. We're saying that the 0 line is right at the ball. So above here would be positive and below here would be negative. And I want to figure out the potential energy. Well, if the level of the ball is 0, then your height is 0, which means that your potential energy is going to be 0, because height is 0. Now let's say that we made the ceiling your reference line, and therefore everything up here is positive and everything down here is negative. So now we're saying we have a height of -1 because we are 1 meter down, but we're still going to plug in mass times gravity times height. So we're doing 2 kilograms times gravity of 10 times a height of -1, and we get a potential energy of -20 joules. So notice how when we had the floor as our 0 potential, we ended up with 40 joules. When we had the height of the ball as our 0 line, we ended up with 0 joules. And when we have the ceiling as our 0 line, we end up with -20 joules. So it all depends on where you are labeling your reference line as to how much potential energy you have. Okay, so potential energy has to do with height. The other side of that is kinetic energy, which has to do with how fast you're moving, the speed of an object. The equation for that is right here. Kinetic energy is 1/2 mv squared, not v times 2. That should say v squared. Again, that didn't transfer well. So it's 1/2 mv with a squared, like that. So put that equation into your notes. And these are just some examples of mechanical energy, some people running, an airplane flying, some sort of motorbike going down a ramp. So we can see if you can calculate the kinetic energy here. This is the answer. But if I have a car that's moving at 5 meters per second and the mass of that car is 200 kilograms, can you calculate the kinetic energy? So it would look like this. Kinetic energy is 1/2 m and times v squared. That's times times times, so I get 1/2 of 200 kilograms times 5 squared. So that gives me 100 times 25, which gives me 2,500 joules. So just to restate, total mechanical energy is potential times, potential plus kinetic. So you're going to add those two together to get your total. And what this equation here is, it just says total mechanical energy at the end is your initial energy plus any work that's added into the system. And we'll talk about work next time in class, but go ahead and put these two equations down in your notes. Here's a great example of how mechanical and or potential and kinetic energy add up to equal your total. So here I have a potential energy of 100 joules. That has to do with the height of this ball. And I have a kinetic energy of 0 because it hasn't started moving yet. So here the height determines your potential energy. Your total energy is going to equal 100 joules for the whole trip because energy is conserved. So as you can see at the top, my potential is 100 and my kinetic is 0. As that ball falls, you can see halfway down that my potential and my kinetic are split 50-50 to equal my total of 100. And then as that ball falls into the water, you can see that I no longer have any height, which is a potential of 0, and all of it has gone to kinetic energy, which means this is where it's going fastest. Here's a practice problem. 0.2 kilogram ball falls off of a cliff, and ignoring air resistance, we want to see the speed at which it strikes the water. So what you would first do is you figure out your potential energy, because potential energy is mass times gravity times height. So I take my 0.2 kilogram ball times a gravity of 10 times a height of 8 meters. And I get 16 joules. Since it's not moving at the top, I have a kinetic energy of 0. And I know that my potential energy at the top is going to equal my kinetic energy at the bottom. So I have 16 equals 1/2 mv squared. So I get 16 equals 1/2 of 0.2 v squared. Solve for v. I get 12.65. Now what you should do is make sure you share your note with whoever was letting this play, and then you're going to move on with the other assignments for today. Have a good day.